Alright, so as I was saying, congratulations on getting into NC State. Let us go on. Let's see here. And that's still funny every time. See, we define the lower central series of a Lie algebra to be series with the following terms. So this was, the series we had last time was kind of similarly defined. To start out the same way, first of all, L1, notice it's 1 without parentheses this time. Is L prime the derived series? Okay, so that was the bracket of L with L. And then the kth term in this lower central series, as it's called, is the bracket of L with Lk minus 1. And that's for k greater than or equal to 2. Right? So thus, L contains L1, which contains L2, which contains, well, you get the idea. Alright. Let's see, was the containment the same way in contrast to the, what we talked about last time, the derived series? Yeah, the derived series had the same pattern, just with, it was defined differently, right? Yeah. But parentheses, it was the same same containment pattern. Okay, now what he says is, as the product of ideals is an ideal, Lk is even an ideal of L. It's not just an ideal of Lk minus 1. So the reason for the name central series comes from the fact that Lk quotient by Lk plus 1 is contained in the center of, so let's write that down here. So here's a little factoid for you called central series as the quotient of Lk by Lk plus 1 is in the center it's in the center of L mod Lk plus 1. Okay. So I guess that we get that each one of these is, of course, the derived algebra is an ideal, right? Is that right? I think one of the things we proved was that if you had two ideals, I and j, then the bracket of I and j was also an ideal. Is that right?
I think so. Yeah.
Or do we need more conditions? Excuse me. I'm a little rusty. Well, we had theorems about solvable ideals last time, but how can you combine old ideals to make a new ideal in general? And we have theorems about quotients of ideals, right? And oh, no, this is called the product of the ideals. I like bracket of L with L would be product of L with L, but the sum of two ideals is an ideal. I plus j is an ideal. I and j are ideals. Oh, and he claims that you're right, this is the product of two ideals is an ideal. That was one of the first things we proved when we first met. All right, it came from the Jacobi identity. It wasn't entirely trivial, but okay. Getting back to task here, we need another definition, which is what? Definition. A Lie algebra L is said to be nilpotent nilpotent. If for some m greater than or equal to 1, we have what? The lower central series truncates to 0, right? This is equal to 0. Let's see, what did we define last time? What was the case if the, what was it if the, last time we defined solvable, right? Solvable was that L parentheses m was equal to 0 for some m. It said L solvable. And I think it's useful to have both of these defined in the same place for just a second. So the series, the solvable series, which was defining solvability, looked a little bit different, right? What did it look like? It looked like, so L1 was still L prime, right, which is L with L. But then like L2 was, L prime with L prime, which by the way is brackets of LL, bracket LL. So in contrast, up here, you're always just bracketing, to form the next one, you're always just bracketing with the whole of the algebra. That's the difference. All right. Okay, so what are examples of nilpotent Lie algebras? Well, the one that we labeled N, strictly upper triangular matrices over a field, is nilpotent. So for example, you could look at N. I'll just keep it simple. I'll do 3 by 3. So you have stuff like 0, 0, 0, 0, 0, 0, A, B, C, right? Things of that form. And you can do it over field. Let's see, some field F. And so if I take the bracket of two such things, right? What do you get? You get well, you get zeros. Let's see, then I get AX, right? 0, 0. I'm going to do the difference of two. And then AZ, it looks like. And then what? Let's see here. I'm trying to do matrix multiplication. I'm doing it badly. That times that. This gives me. Oh, wait a minute. Excuse me. There's the middle column is 0. I'm an idiot. Look, this gets 0, 0, 0. So it's 0, 0, 0. Then that one, the third one, I just get AZ, and then I get CZ, right? No, I don't even get that. I get 0. I'm an idiot.
Zeros.
I get zeros all around, and then
The other one's going to be the same thing. 0, 0.
oh yeah,
0, 0, easy.
yeah. I think I get, so like this
You get CX.
times that. I think I get CX, yeah. And then zeros. But oh, you mean the same? Yeah, the same sort of thing, but I mean, it's not exact. I was
Right.
thinking you're saying the same exact thing. That's not what you meant. So the bottom line is we get zeros, 0, 0, and then stuff up here. Right, so it's just in the 3, 3. And so this is a typical thing in L prime. And if you take two such things, if you take 0, 0, x, 0, 0, 0, 0, 0, 0, and bracket it with 0, 0, y, 0, 0, 0, 0, 0, 0, right? And you calculate the bracket of such things, you get, of course, definitely get first two columns being 0, because they're both multiplied with, I mean, columns are preserved. And you also get the first two rows being 0 by the same, like the other side of the matrix multiplication. And those are zeros as well. So, therefore, although, oh, I'm sorry, this just shows that L brackets 2 is equal to 0 now.
Right.
So that means that L is solvable. We need to check this with L itself, right? So yeah, so we should really look at, if I had more of a brain. All right, so here, let's see, 0, x, y, z with like 0, 0, a, 0, 0, 0, 0, 0, 0. You know, what's that bracket? So obviously we get definitely these are zeros. I'll think about this one times that one. I get a middle column of zeros,
Yeah, you should get all
and I get a
zeros.
third column of zeros from the this times that, and that times this. I get 0 second column. Yeah, it's zeros, and you could work it out. But so therefore, that tells me that L2 is equal to 0, which tells me, you know what? So it is nilpotent. Okay, so that's an example of a nilpotent Lie algebra. Furthermore, any nilpotent Lie algebra is solvable. All right, so that's a claim you can make. However, not every solvable algebra nilpotent. Yeah. Oh, following my usual bad habit, I numbered it at the end. It's page number 1, though. It's hard to miss. Page number 2. So it was a claim. Claim. What was it? Nilpotent implies solvable. Right? And the proof of that, he says, is what? It's
Induction. Okay.
yeah, he says prove by proof. Use induction on K. To show that the derived series is a subset of the lower central series at each order. Let's see here. So for k equals to 1, we just have, I mean, there,
Yeah.
k equals 1, it's kind of, not,
One,
yeah.
just-
Oh, yeah. L1 is equal to L1, so therefore, of course, L1 is a subset of L1. Yes, okay, great. L parentheses 1 is a subset of L1. Finally, parentheses, parentheses, parentheses. All right, next, assume that L of n is a subset of Ln for some n. For k equals to n, greater than or equal to 1. Consider we want to show L n plus 1. We want to consider that set ln plus 1 is defined to be what? L is equal to L parentheses n, L parentheses n. But this, of course, by the induction hypothesis, is a subset of L with, and we're using the product bracket subset theorem again. It should have a name. I don't know if that was ever stated explicitly earlier. I mean, it might have been in there somewhere. I don't remember.
Yeah.
But there's that, right?
Mm-hmm.
But
Not use the induction hypothesis.
oh, I haven't. Yeah, oh, sorry. I haven't used the induction hypothesis yet either. To use the induction hypothesis, I should have put an n there. Yeah. Oh, but that is ln plus 1. So we're done. Yeah. So I proved by mathematical induction. Got it. Now the standard example of something which is solvable but not nilpotent. So there's, it's not if and only if. There's, he says to look at B and F, the so-called just upper triangular matrices over F for n greater than or equal to 2. So if 2 works, let's look at 2. So 2 would be something like A, B, 0, C. So if we take 2 of those guys, A, B, 0, C, and take the bracket with X, Y, 0, Z, I think the thing I've learned is it's easier just to write it out. I could try to do it in my head, but I think that my head, I'm not Euler. I'm not blind. I don't need to. There's other ways I'm not Euler. But anyway, let's hear. Okay, so that was what? That's you got yourself AX, right? 0. And here you got, yeah, AY plus, yeah, BZ, thank you. And then you got yourself a CZ. Over here you got AX. And then you got 0. You got BX plus CY, and you got CZ. So let's see. Oh, the AX's cancel. So it's not simple, right? Like,
Yeah.
The derived algebra is not just the algebra again. But it is a little bit different than the one we just worked out, because you gotta... Oh, wait a minute, is it? I don't know. I'm not sure I believe him. CZ's cancel too. I'm just left with something of the form star. Like this again. Oh, but part of what?
When you multiply, yeah.
Okay, but then I should look at
Yeah, it'll give you the star again.
AB0C with 0, Y, 0, 0. So basically just set X and Z to be, same calculation, but just set X and Z to be 0. Right, so what we have is what?
0, Y, AY, 0.
It's 12 o'clock p.m.
AY.
Silence, woman. AY, oh, minus C, AY, yeah?
Are you multiplying these?
Oh, I'm thinking about using this formula. I can not reinvent, since I already worked out the multiplication for X and Z being whatever. Now they're 0, so
Yeah.
they're still, I mean, they're
It's just AY.
AY.
Yeah.
Oh, but there's a CY over here too.
C0.
Y is not 0.
Oh. Yeah. If we compare these two, in this case, C is 0. For multiple.
No, but the C is over here. I've used ABC in the same way.
Are you doing this matrix first or this one first?
This one gives me the AY. And then the other one,
okay.
and then of course in terms of just the the matrix multiplication, it's the when you think about this times that.
I thought you were doing both multiplications. I thought you were doing this one and this one.
Oh.
That's why I was like.
Oh, I'm sorry.
That's okay.
So if I take this times that, switched around, I end up with that CY, but the commutator says minus. So, but as you can see, that is an element of. So this is a typical element of the derived series, right?
Right.
And so this is L. How can I say this? Well, this is the derived series again, right?
Yeah.
So basically that tells you that L1 is equal to L1, and then L2 is equal to L3, is equal to L4, and so forth and so on, forever and ever. It's always equal to that derived algebra. So it's not
Never 0.
it's not nilpotent. Yeah, this is not nilpotent. Okay, now that we got that done. So I think it is important to spend a couple minutes on examples, even when they're silly. Examples are helpful. And understandably, people who write books like this typically don't include these kinds of details in the books because they're really boring to read, and you should work them out for yourself. They're probably even more boring to watch, but oh well. It's okay. Certain people make choices. I have to live with them. Certain people. Oh, where are we? Yes. Oh, lemma. Not a lemma. A lemma 4.9 says the following: L Lie algebra. I'm not even gonna write that. L is a Lie algebra. I'm tired of writing that. A. If L is nilpotent, then any subalgebra of L is also nilpotent. Well, that's nice. Just like the solvable case, right?
Mm-hmm.
And then B, although he has not told us that the homomorphic image of a nilpotent algebra is nilpotent, that he did not say. You would think he would say that here if it was true. I bet it's not. Anyway, if Z, if L mod the center of L is nilpotent, then L is nilpotent. So it's kind of a cancellation kind of thing. If you have this particular quotient is nilpotent, then L is nilpotent. Okay, so here we go. Excuse me. Proof. He says A is
I like his proof.
proof for A. This is clear from the definition. Alright, well, humor me. If it's so clear, it should be easy to write down. Suppose...
You have to use containment.
Probably. See, what we need a letter for the algebra. Let's let I be a subalgebra. Oh, I is usually an ideal. I just want a subalgebra.
Use curly L.
Curly L. I'll use this one. There you go. So, suppose L is a subalgebra of L, which means that L is a subspace. Oh, good grief. L is a subspace of L, and the bracket of L and L is a subset of L. Ah, so many L's. Nilpotent A. L is nilpotent. We're given L. What have you done to me? I'm going to put a tilde on that. There, it's all better. Haha. We're given that L is nilpotent. So we wish to show that L tilde is nilpotent. Alright. So L tilde, what would L tilde 1 be? That would be the bracket of L tilde with L tilde, right? Which of course is a subset of LL. L tilde 2 would be L tilde 1, which would of course be a subset of L and L1, which is, this is L1 by the way, okay. L1, and then L tilde 3 would be L tilde with L tilde 2, which by the way would be a subset of, oh by the way this is L2. So L2 contains L2 tilde, so this is a subset of an L tilde contains an L. So as you predicted, it is in fact an abusive manifold use of this subset product theorem thing, which is L3, etc., etc. So thus, we have L tilde k, subset of LK for k in the natural numbers, but Lm equals to 0 for some m greater than or equal to 1, therefore L tilde m is also a subset of 0. Oh, for some reason I'm using 0, but I've gone back to less degenerately denoted 0, which we're in our current notation is 0. So, okay. Yay. As you said, it's clear from the definition. Okay. Which is another way of saying I don't feel like typing it out because it's just not that interesting.
Yeah.
So, yeah, that's fine. It wasn't hard. Okay, by induction, in a variation of exercise 4.1, we can show that L mod the center of L is equal to LK plus CL mod CL. So if the quotient is 0, then LM is... This is like that other proof we did. This smells like the proof we went through for part B of the lemma 4.4. Or maybe part C. Part C. No, part B. I meant part B. Alright. Let me foolishly attempt to figure out what he's saying here. Okay, which I'm sure is a perfectly reasonable argument. So proof. We're attempting to show part B, which is to say that if L mod the center of L is nilpotent, then L is nilpotent. Just realized that this was up against that, which means when I write it was shaking it. Oh well. Alright, so what's he say? What's his proof? He says you can show that L mod the center of L, the kth lower central series of that is equal to, I wonder if he really means equal to, Whenever I read equals to, I always wonder, does it really mean isomorphic to? But he probably means equals here. Let's see. At least they're both quotients, so there's hope about the equality. Right. Now, if we can show this, I do agree with his follow-up, right? If this is true, so just take this, let's take this as an identity star for a second, okay? So given star, you notice that if L mod ZL, so you'd have L mod ZL, say to the M equals to 0, that would imply that L M plus ZL mod ZL was equal to 0, right? Which would actually tell us what?
That L to them is 0.
No. It would tell us that LM was a subset of the center of L. But then one more step. But LM plus 1 is L with LM, right? And if that's, a subset of L with ZL, well, L with ZL by definition is 0. So therefore, LM plus 1 is equal to 0, which shows you that it's nilpotent. So it boils down to star. How do we show star? He says by induction or a variation of exercise 4.1. Did we do exercise 4.1? We did exercise 4.1 was that the homomorphic image of the kth derived series was the kth derived series of not quite that,
Well, we need lab manuals today.
I don't know.
Well, I mean, there is a physics lab.
Yeah, I don't know.
You don't know. That's great, because mine's in my dorm room. You need to know if I want to.
Well, I mean, do you have a lab partner?
Yes. I have the lab manual. It's back in my dorm room. I'd forgotten to bring it.
Well, if your lab partner has theirs, you should be fine.
No, we only have one between the two of us.
I think one of you needs one.
Okay.
Sorry.
Thank you. Bye.
Yeah. I'm not sure, really. No. Okay, so we're trying to show this.
Yep.
So how can we show that? Let's see, is it for k equals 1, what do we have? We have the claim that L mod ZL 1, which is what? That's the bracket, right, of L mod ZL with L mod ZL. The question is, why is that equal to the bracket of L with L plus ZL mod ZL? I think the answer is essentially just by definition of this, like a typical point in here is something like, x plus ZL, y plus ZL, right?
Mm-hmm.
Take the bracket of those, you get something like x comma y plus ZL, which is exactly something that's in LL plus ZL, and you can go the other way with that too. So these are equal as sets because then they're well, quotient, I mean, of course, but that's the thing upstairs. All right, so that's 1. So he says you can do induction. Do you see how to do it?
I'm not sure.
K equals n. So we have L mod. So let's suppose that this is true, right? And then consider so that would be L with except that it wouldn't be that, would it?
Mods, yeah.
Okay. But this is equal to, by the induction hypothesis, which through essentially the same calculation as up here is equal to
Right.
L with Ln. Which of course is Ln plus 1 plus ZL or ZL. I haven't been terribly careful here, but I think you can see how to make it careful. Yeah. Okay, so getting back to work. Okay, so then that shows that if if L mod the center is nilpotent, then L is nilpotent. All right. Remark: the analog of lemma 4.4b does not hold. If I is an ideal of a Lie algebra, it is possible that both L mod I and I are nilpotent, but L is not. So in other words, it's important that we mod it by the center. Not just any ideal will do. We needed the center because this step right here, having it that it's the center of the whole algebra, is mission critical, because we're taking products with the whole Lie algebra, not like just things in the series, the derived series like the other one. The other one, because we work with the derived series, we're working with not L here, but something smaller. So it sufficed to just have information about an ideal as opposed to the whole algebra. So you need the center here to make this work. But an example he said is the two-dimensional non-abelian Lie algebra. I guess he's saying there's an ideal. That ideal is nilpotent, and the L mod, the thing, is nilpotent, but the two-dimensional non-abelian Lie algebra is not nilpotent. So, I mean, the ideals of the two-dimensional non-abelian Lie algebra, I guess they're one-dimensional, so the bracket is trivial. So they're both like L2 is 0, so they're nilpotent.
Yeah.
But the whole thing's not nilpotent because I don't know, I'd have to look at that actually. But I'm not going to. Until we turn off the camera, in which case we'll look at it. Carefully. So, page 5. Look ahead. Alright, so I'll look at The previous suggestion suggests that we might have a chance to understand all the finite dimensional Lie algebras. The radical L of any Lie algebra is solvable. And the L mod the radical is semi-simple, right? So, given any Lie algebra, L, finite dimensional, okay. We have the radical of L is solvable. And we have that L mod the radical of L is semi-simple. Right? Now, what did semi-simple mean? We haven't talked about that today. Semi-simple has that the radical is 0. So the radical of L mod the radical is automatically 0. So, which in this particular case means that rad of L mod rad is equal to 0. Which in words means that the only solvable ideal of L mod the radical is 0 itself. It's the trivial ideal. So no interesting solvable ideals in the semi-simple case. So what he says then is, so to understand L, it's necessary to understand two things, right? Number one, an arbitrary solvable Lie algebra. And number two, an arbitrary semi-simple Lie algebra. Right, so why is that a reasonable statement? Well, I guess you can get a solvable the maximal solvable ideal, right, is the radical. It's the largest solvable ideal. So if you can understand what's possible for that, that gives you a sense of what that radical can be in arbitrary Lie algebras. And if you know that L mod the radical is semi-simple, so L mod the radical is basically everything in the Lie algebra except for the solvable piece. Like intuitively, that's what the quotient is, right? Mm-hmm. Setting that solvable piece to be kind of the 0. So if I can say what's possible in the semi-simple case, then that means that's everything else. And then, so we have that underlying basic quotient vector space idea that if you have, if I have V is equal to, say, V1 direct sum V2, right, then I have that V quotient V1 is isomorphic to V2 and vice versa.
Right.
So essentially,
You have it. Yes, one for me.
oh, okay, cool. So basically, if we can understand what the possibilities are out there for V1 and V2, then you can get a sense of what the possible V is, because we can build them back like this. Thinking of V1 as being the radical and V2 as being everything else. Semi-simple piece to the algebra, yeah.
Thank you. Yep.
That brings us to our next, latest, greatest definition.
See you later.
See you, Sean. Definition. the Lie algebra is simple if it has no ideals I guess it's like it's got to show an E or something. I don't know. I don't have cable. I just some of the people say if it has no ideals other than 0 and L, and it is not abelian. As he mentions here, the restriction that the simple Lie algebra may not be abelian removes one-dimensional abelian Lie algebra. Without this restriction, the Lie algebra would be simple but not semi-simple. And that is not really what you want.
Yeah.
So. All right, so he mentions here that historically the answer to 1, like what's an arbitrary solvable Lie algebra? So this was found by Lie. Lie figured that out back in the probably 19th century, and essentially you can, up to isomorphism, you can saw these as subalgebras. I can't spell algebras of upper triangular matrices. Okay. And so you can model them if you like. By upper, there's a one-to-one correspondence between those guys and upper subalgebras of upper triangular matrices. And then the simple, so I should say the why do you care about simple? The one thing I've forgotten to write down here, but it's important to this story, is that you can build semi-simple algebras from simple algebras. Okay, the simple algebras are like the fundamental building blocks of the semi-simple algebras. So the here's the theorem. Every semi-simple algebra, semi-simple Lie algebra, is the direct sum of simple Lie algebras. Direct sum in the sense of linear algebra. So as you can see then, the ball gets pushed to the problem of, the classification question then boils down to what are the simple, what are the simple Lie algebras, right? Mm-hmm. So what are the possible simple Lie algebras? That's a major theorem, and as he says, the proof is based on the work of Killing, Engel, and Cartan from around the turn of the century, give or take. It's 1880 to 1910 where this stuff got fleshed out. But once the dust settled, we learned that there are 3 infinite families over the complexes. Now, I guess the story over other characteristics is still unfinished. Yeah. There's ongoing work in the classification of the algebras over non-characteristic fields. But here he goes. So with 5 exceptions, 5 exceptions, that's weird, right?
Yeah.
5 exceptions. Every finite dimensional Lie algebra over C is isomorphic in the sense of Lie algebras, of course. Lie algebra isomorphism, right? Preservation of linear structure and bracket, to one of the classical Lie algebras. Or the matrix Lie algebras, if you like. In particular, you have SL, NC, you have SO, little so, NC, or you have little sp, 2NC. And the five exceptions are the so-called excuse me, E6, E7, E8, F4, and the famous G2. All right. Now, and then he describes the definition of these classical Lie algebras, as I will do shortly. But rather than do that, I'd like to say a word or two about their relation to Lie groups. At this point, this is not in this book, as far as I know. But I think any presentation of Lie algebras benefits a little bit from at least some discussion of Lie groups. So let me just tell you a few unjustified things here. So each one of these Lie algebras is the tangent space, can be realized as the tangent space to a corresponding Lie group. Like this guy is the tangent space at the identity to what's called big SL, NC. This guy can be realized as the tangent space at the identity of big SO, NC, I think. I know at some point I'll open up the other book that has details. There's some issues with real versus complex, and I may be, but anyway. This is either true or very close to true. So, doesn't seem quite right what I said there. The tangent space at the identity to the so-called symplectic 2NC. Now each one of these groups without the T's, okay? So like SLNC, SONC, SP2NC. These are all groups in the sense of, well, group theory. SLNC, this is just, so you're looking at, like X in GL, the general linear group, NC, such that the determinant of X is equal to 1. And so the way I think about it, so let me just focus on this one for a second. So if this is sort of the Lie group, right? Somewhere in here, there's the identity matrix. And you can think of, at least conceptually, you can think of there being like a tangent plane here, right? Mm-hmm. And so if you take a path in the space of SLNC, it would look something like this, right? And it turns out that you can parameterize paths through the origin by something like e to the, so you can say like this is the path is gamma. And I could say something like gamma of t is equal e to the tb. Right, where this is the matrix exponential. These are matrices, so matrix exponential is defined. And certainly when t is equal to 0, we get gamma 0 is the matrix exponential of the 0 matrix, which of course is the identity matrix. So as you can see, this is in fact, honest to goodness, a curve through the point I at t equal to 0. What's its tangent? Well, it's easy enough to calculate. You can take derivatives. Gamma prime of 0 is equal to what? Well, exactly, what is it equal to? Well, it's equal to b e to the tb, evaluated at t equal to 0. In other words, gamma prime of 0 is b. So the thing that parameterizes the curve through the identity and multiplies the real parameter t is not just any old thing. In fact, if you believe me about that being the tangent space, b is an element of SL and C. Now, so to make this story optimally interesting, what is SL and C defined by? Well, you also have this, right? You have that the determinant of e to the tb is equal to 1 for all t. Because it's in this is a curve in SLNC, the determinant 1 matrices.
Mm-hmm.
But there's a beautiful identity that relates the determinant to the trace in the exponential, and here's how it goes. So the determinant of the exponential of b, it's equal to the exponential, ordinary exponential, garden variety exponential, of the trace of tb. And so, you know, you can pull the t out, right? This is, I think I've muddled this argument a little bit, but that's e to the t, e to the trace b, right?
Mm-hmm.
Multiply t over the other side and take t equal to 0. Well, when we take t equals to 0, we get what? 1 is equal to e to the trace of b. Therefore, the trace of b is equal to 0. So you notice oops, sorry, I'm writing where you can't see it. So what we have then is that the trace of b is 0 as a consequence of saying that the group, the special linear group of matrices, has determinant 1. So the fact that the tangent space is connected to the group at the identity has forced the traceless condition on us, as opposed to this book where we just defined them to be traceless for the sake of having an example, which was fine. Now, these other guys, like, you know, SO, these are the special orthogonal matrices. So these are rotations which have determinant 1. The symplectic preserve the almost complex structure of something. There's again a group of transformations. These are all tied to some sort of geometric transformations, which is in part why Lee was interested in them.
Yeah.
And then probably, what's his contemporary there? The Erlangen program. Who was that? Klein, right? Klein's geometry program. So that's page 6. So anyway, okay, so we already know SLN, that's the traceless n by n matrices. SO, this SON, see the other kind of simple, the algebra, allegedly. I'm telling you it's equal to the tangent space at the identity of SON. Let's see, if we believe me, SON is a, let's see here, in ONC, see, this is where I'm a little bit shaky because I'm not sure if I'm supposed to use the Hermitian thing or the other thing. Let me postpone proper discussion of this until I have everything, all my ducks in a row. I don't want to send you down the garden path here. Anyway, he defines excuse me. Well, he says that they're all special cases of this GL sub S NC, where he's defined them to be X in the basically n by n complex matrices GLNC, such that the transpose of X times S is equal to minus S times X. So he's like, okay, so there's some different cases you can look at from this. There's an exercise which shows that that forms a Lie algebra, right, of GLNC, a sub-Lie algebra of GLNC. So one of the examples that you can take then, once you have that this is a Lie algebra, is S is equal to 0, the IL identity, the IL identity, L by L, right? So this is a 2L by 2L matrix with L by L blocks. And he says that defines SO